My name is Dr. Stephen Cochrane. I'm a senior lecturer in organic chemistry in the school, and I'm also the head of outreach. So why should you think about studying chemistry, medicinal chemistry, or chemical engineering? Well, these topics are at the forefront of efforts to tackle some of the biggest challenges facing us in the 21st century. Examples include clean water. How do we make sure that everyone in the world has access to clean water that doesn't make them sick? Well, disinfectant methods and ways to treat water in the drinking water system are things that are tackled in chemistry and chemical engineering. Another major problem is climate change. What do we do about all the CO2 being released into our atmosphere by burning fossil fuels? Well, CO2 is actually a fairly useful chemical. If you've got wood around you, that wood was effectively made by the growth of trees, which took in CO2 from the atmosphere and in the process of photosynthesis grew. So in chemistry and chemical engineering, we look at ways to capture CO2 and utilize it to make useful chemicals. Another challenge is diagnosing disease. So how, as chemists and chemical engineers, can we tackle this? Well, as chemists specifically, we can come up with new methods to detect various markers that can be a sign of disease, whether this is small ions like sodium or potassium, or larger molecules like antigens, which could be present on the surface of a virus. Food security. How do we make sure that we have enough food to feed a growing population? Well, this could be things like coming up with selective and non-toxic pesticides, or studying the signaling pathways within plants to be able to make them grow quicker and grow bigger to feed the population with a finite amount of land that we have here on the earth. Sustainable energy, of course, is another thing. How do we utilize natural resources, things like wind, solar, and get this energy stored? Well, we need efficient batteries, and how we make those batteries is directly in the realm of chemistry and chemical engineering. And then, of course, there is treatment of disease, and this is where chemists and medicinal chemists are right at the forefront. If you ever get sick, it's not the doctor, it's not the pharmacist who cures you, it's the chemist or medicinal chemist that synthesize that drug that is going into your body and treating said disease. So what are the different pathways in our school? We have medicinal chemistry, and medicinal chemistry is the interface of chemistry and biology. And this is primarily focused on drug development and design. It shares some common themes with the chemistry degree, but as we'll see in the next slide, it does take other elements more in the realm of biology. Chemistry, this is a core subject, and it's the study of matter. And chemistry is essential to innovation and technological developments. Chemical engineering is making what we need on scale, and this covers all manners of different things, be it bulk chemicals, fine chemicals, all of these materials which are used to make various things we use, like plastics that go into making reusable bottles, all these different types of things. The processes that make the chemicals that go into these materials are done by chemical engineers. So what does each pathway involve? Well, on the left, we have chemistry. And within chemistry, there's three core areas. There's organic, inorganic, and physical. And then there's also analytical chemistry, which usually has a combination of the first three. You'll cover these in increasing levels of complexity through a chemistry degree. There will also be a final year research project where students will undertake research in a academic's lab, really getting excellent experience in that particular research area. There's the option for a year in industry, and also the option for taking it at either the BSc or the MSci level. Medicinal chemistry, it follows much of the same format as chemistry, but it does take additional modules in, for example, bioinformatics and genetics. These are very important as kind of next generation predictive tools for finding new drugs, and also looks at things like how do we design drugs and how do we model interactions with a drug molecule and its target. And then this also has the option to take a year in industry or to do an MSci or BSc degree. Chemical engineering, key topics covered in this course include looking at processes, heat and mass transfer, reactors, design of various components within processes. And again, this can either be a B-Eng or an M-Eng degree. And you have the option of doing a year in industry as well. And all of our courses are accredited by the relevant bodies, with the RSC for our chemistry degrees and the Institute of Chemical Engineers for our chemical engineering degrees. Okay, so I couldn't not mention really just how essential chemistry is in the current climate we're facing with COVID-19. Of course, this has changed a lot of things for us. The reason I'm giving this talk virtually rather than in person is because of lockdown measures to prevent the spread of coronavirus. In chemistry, chemical engineering, and medicinal chemistry, we're right at the forefront of the effort to tackle these types of problems. So for example, on the left-hand side here, what we have is the spike protein on the surface of the SARS-CoV-2 virus. This is the virus that causes coronavirus infections. And as chemists, we all understand completely what the structures of these things are. These proteins are made of amino acids. We can understand the types of structures amino acids adopt into proteins. And using molecular modeling, here we're simulating an interaction between the spike protein and part of the receptor on a cell. And this is what's going to have to happen for a cell to be infected. If we know how the virus interacts with the receptor, we can rationally design ways to interrupt this interaction, therefore inhibit the virus entering the cell, and act as a treatment to prevent coronavirus infection. For chemistry and medicinal chemistry, we can look at how do we synthesize molecules that could be therapeutics for treating coronavirus symptoms. You'll have heard a lot about these molecules. In fact, most people walking around in the street will have heard of them. But as chemists, medicinal chemists, chemical engineers, you'll be part of a few people who actually can look at these molecules, understand what they are, what they do, and how you can make them. Chemical engineering, in particular, this is extremely important for making things on scale. So for example, a lot of efforts right now are going towards developing vaccines. The materials are going to go into these vaccines, as well as the production of the vaccines themselves, are going to be largely attributed to the efforts of chemical engineers. Also, PPE, personal protective equipment, these are made from polymers for the most part, polypropylene, polyethylene. How these feed materials are made inside plants on scale is all in the realm of chemical engineering. So I hope I've convinced you with this slide just how important these topics are for relevant 21st century problems. So what about our school? Well, Queen's University Belfast is a member of the Russell Group. The Russell Group is effectively a group of universities in the UK that are research intensive, and there's 24 in total. As a school, as a joint school of chemistry and chemical engineering, we're top in the UK. And in our school, we have an excellent staff to student ratio, which is very good for learning. It means that one lecturer can effectively spend more time per student than if you were in a much larger institution. In the last Research Excellence Assessment, 80% of the research conducted by academics in our school was ranked as either world-class or internationally excellent. And that's important because it means that you're being taught by people who are advancing our knowledge in these areas and really know their subjects well. And for the most part, your classes will take place in the David Keir building, which is shown here, and has entrances on the Malone Road and Stranmillis Road in Belfast. A big advantage in Queen's University Belfast is that it's a city campus, which means it's quite compact and easy to walk around. So at most, if you have classes in the David Keir building and then some across, for example, in the NBC in the Lisburn Road, at most will take you 10 to 15 minutes to walk there, which is great exercise, and also it's good that you're not having to travel too far between different areas. It's also very close to a number of different things like student accommodation, the city centre. If you're like me and love running, it's also very close to a number of parks, Botanic and Ormo, as well as the Lag and Towpath, which runs the whole way into Lisburn. So our school's mission is health and sustainability. And as I mentioned, we have a number of world-leading academics, and I'm just going to profile a few here. So Dr. Chung-Fei Wu is a chemical engineer, and his research specializes in turning waste plastics into useful materials. Dr. Nancy Ardioli is another chemical engineer, and her research focuses on carbon capture and utilization. Dr. Leila Moira is a Academy of Engineering research fellow, and her research specializes in liquid engineering for separating different gases. And my own research, we look at synthesizing next generation antibiotics to combat antimicrobial resistance. So what about our school and its facilities? Well, we really do have excellent facilities here at Queen's. In recent years, a number of them have been refurbished. For example, this is one of the lecture theatres that we have that has a nice big screen that actually has multiple different smaller screens within it and allows video conferencing with many different feeds from around the world. So yeah, really good facilities for teaching. We also have state-of-the-art research facilities, which as undergraduates you'll also use as part of your degrees. So the school has several NMR spectrometers, that's nuclear magnetic resonance, things we use for characterizing chemicals that we synthesize, things like drugs or polymers for various applications. We have numerous mass spectrometers as well as scanning electron microscopes for looking at the structure of compounds using X-ray crystallography. And very recently, the school opened a new pharmaceutical analysis laboratory. This is it shown here. It is a number of pieces of equipment called high-performance liquid chromatography machines, and these are for looking at or for analyzing various pharmaceutical samples. It could be, for example, drugs that have been synthesized, or looking at the progress of chemical reactions that are being used to make a certain product. So we have very excellent facilities in the school. And I also mentioned how you're taught by global experts, just to pick out one. So this is Professor A.P. De Silva. A.P. is a legend in the school. He actually taught me when I was an undergraduate in the School of Chemistry and Chemical Engineering. And as part of his research, he invented a blood electrolyte monitoring device. And this was taken up by Roche. And it has resulted in saving thousands of lives every year and brought in over $500,000 in terms of revenue. And AP actually teaches physical organic chemistry at Queen's. And this design is all based on a single molecule that can very effectively tell the concentration of ions, things like sodium and potassium, which is important for looking at their levels in blood samples. And that's what this little device does, shown down here. A big advantage of our degree pathways as well is that they're incredibly flexible. So chemistry and chemical engineering have a common first semester. It means that if you start in chemistry and you decide after the first semester, you know what, chemical engineering is more of my thing, you can switch, and the same vice versa for chemistry. For medicinal chemistry, because this has a lot more biological content, it's not possible to switch to chemical engineering from that. With both degrees, you can either do a 3-year or a 4-year degree pathway, a 3-year for the BSc or the BEng, and a 4-year for the MS or the MSci or the MEng. It is possible to switch to the MSci or the MEng if you start in a BSc or a BEng, and this is simply requires you to have a certain grade come 3rd year to enter a 4th year. Students can also opt for an industrial placement, where they go and work for a company for a year and then return to finish their final year at Queen's. And the big advantage of this is students, when they return, they complete their degree, and then they often go back to that employer for a position. So it's kind of a way to get your foot in the door for a good company. And in terms of industrial placements, Queen's has connections with local and overseas industries, and so as a school we can put you in touch with prospective employers as well as students who either work there or have done placements in these companies before, which allows you to get a really good idea about what they can expect on with a placement at that company. And whilst on your year in industry, you'll be paid. and you're only required to pay a nominal tuition fee at Queen's for that year. Another big advantage of being in Belfast is that you're typically within an hour's flying time of most major UK cities. And in terms of career prospects, graduates from our school do very well. In 2016, we were the 5th best for employment in chemistry in the UK and the 6th for chemical engineering. And in over 95% of Queen's graduates are in employment or further study 6 months after graduation. Another important thing to us as a school and to Queen's as a whole is promoting equality and diversity. You should be capable of doing the degree that you wish to do, regardless of your background or circumstances. And the way that this is often acknowledged is through receipt of Athena Swan Awards. So an Athena Swan Award, it recognises advancement of gender equality in terms of representation, progression and success for all. So our school was awarded a Silver Award in 2010, and this was renewed again in 2017. And as you can see from our female to male ratios, especially for medicinal chemistry, we are doing quite well in terms of trying to have degrees open to everyone that are balanced. Okay, so just to finish off my talk, I want to give you an idea about what a typical or what a career trajectory could look like after you graduate from Queen's or from the School of Chemistry and Chemical Engineering. And I'll look at myself because obviously I'm quite familiar with my own background. So I graduated from Queen's in 2010 with an MSc in chemistry. I had a lot of opportunity to do things during my degree. One thing that stood out was during the summer between my 2nd and 3rd year, I went to University of Oslo with an organisation called IESTA and did a placement in a lab there for 2 months, getting experience in organic chemistry. Upon completion of my degree, I moved out to the University of Alberta, which is in Edmonton, Alberta, Canada, and I completed my PhD in organic chemistry there. Certainly that was a great experience, very different than living in Northern Ireland. That picture there is of an ice festival that I was at, because in the winter in Edmonton you typically drop down below -10 in about the end of October, and then it usually sits around -10, -20 until about March, sometimes even dropping to -30 or -40. So after completing my PhD, I returned to the UK and I worked as a postdoctoral research associate at the University of Oxford for a year. And during this time, I was involved in some work looking at developing new drugs to treat tuberculosis. We did find something quite successful, which is patented and currently undergoing trials. And then at the end of that, I returned to the university I love so much, Queen's, and now I teach organic chemistry and chemical biology here. So that is the end of my talk. Thanks for watching, and I will be happy to answer any questions you may have.